Jai Hind students, welcome to my YouTube channel. Students, are you confused about life and the meaning it brings? Do you think that life is so full of complex issues and these things make you wonder if you can really cope with it? Then I must assure you, life is indeed beautiful and you can enjoy every bit of it. There's so much to learn from the process you are passing through. In these times, in this stage which you are going through, you can be aware and conscious of all the lessons that comes with life. You can make the best of these lessons and let them ease your experiences. So students, don't run away. Face each and every adversaries and learn from each and every experiences. It's a gift which has been given to you. Make best use of your life, right? So with that students, let's begin this session. In the previous lecture, we have discussed about Faraday's experiments, right? In all the experiments, what we have observed was, whenever there's a change in the magnetic flux or magnetic field associated with a coil or a loop or an electric circuit, then a current is produced. This phenomenon is known as electromagnetic induction, isn't it? There were some other points which were also concluded. We'll try to recall all those observations and conclusions. And these observations and conclusions forms the laws of electromagnetic induction, which we are going to discuss in this session, right? So let's start with the first law. First law is nothing, but actually it is the definition of electromagnetic induction. That is, whenever there is a change in the magnetic flux linked with the coil, an induced EMF or induced current is produced in it. So that's the first law. So whenever magnetic flux linked with a circuit, it can either be in the form of a loop of wire or a coil or an electric circuit in general, changes, then induced EMF or current is produced. So in order to understand this law, you need to be very much aware of the term magnetic flux. Students, you are aware, theoretically, magnetic flux associated with a surface held in a magnetic field is defined as total number of magnetic field lines crossing through the surface held in a uniform magnetic field normally through it. That is, suppose this is the loop under consideration. And these are the field lines crossing through it normally. So total number of field lines crossing normally through the loop, that gives the measure of the magnetic field. This is suppose the magnetic field. So all the magnetic field lines which crosses perpendicularly through the surface held in a magnetic field, that gives the measure of magnetic flux. Now in this case, suppose the area of this loop under consideration is A. So magnetic flux is simply given by BA. That is, mathematically, flux is given by the product of the strength of the magnetic field and the area of the loop under consideration, right? Provided all the field lines are crossing normally through the loop. All the field lines are crossing normally through the loop. Now in case the field lines are inclined like this, so you can consider a small area over here. So this is the normal, this will be the area vector, isn't it? And this is the magnetic field. Now here the angle theta is having some non-zero finite value. Here theta is 0. We'll consider theta to be the angle between the magnetic field and the area vector. Now students, look, here the magnetic field can be resolved into two components. One in a direction perpendicular to the surface, that is along the area vector. It will be B cos theta. While the other component which is along the surface, this component would be B sin theta. And theoretically we are aware, only those magnetic field lines will contribute towards the flux which are crossing normally through this area, and that component is B cos theta. So here in this case, when magnetic field is inclined, when it is making an angle theta with the area vector or with the normal to the surface under consideration, then the magnetic flux is given by the product of the component of the magnetic field which is perpendicular to the surface area and the area of that surface. So mathematically it can be represented as B vector dot A vector. This is the dot of the scalar product. So theta is the angle between magnetic field and area vector. Clear, students? So mathematically flux is given by the scalar or the dot product of magnetic field and area vector. Right? So magnetic flux, remember, it's a scalar quantity. And in case it consists of n identical turns, the loop consists of n identical turns, then the flux will be given by n times. So for n identical turns, the flux, which is the magnetic flux, it will be given by NBA cos theta. Clear, students? So this is the general formula for the magnetic flux. We have already discussed this topic of magnetic flux in the earlier section. I'll provide the link of that lecture in the description section. Right? So, SI unit we are aware. The SI unit of magnetic flux is Weber. 1 Weber is Tesla into meter square. Right? So, SI unit is Weber and it is Tesla into meter square. This is the number of terms, dimensionless. Cos theta again, it's a dimensionless quantity. So, third case is, students, in case the field lines are all directed along the surface so that it makes an angle of 90 degree with the area vector. That is, in this case, no field line is crossing normally through the surface. So here theta would be equal to 90 degree and obviously flux would be equal to 0, cos 90 being 0. So only that component of the magnetic field contributes towards the flux which is perpendicular to the area of the loop under consideration. Right? So only those magnetic field lines which crosses through any area in the normal direction or perpendicular to the area, that will contribute towards the flux. So now first law states that in order to produce induced EMF or induced current, the magnetic flux linked with the coil needs to be changed. So flux needs to be changed. So how to change flux? What are the ways in which the flux can be changed? First is by increasing or decreasing the strength of the magnetic field. Now look, try to recall the experiments which we have discussed in the previous lecture, where the magnet is brought closer to a stationary coil. So magnet acts as a source of magnetic field. So as it is brought closer to the stationary coil, then the magnetic field lines linked with the coil starts growing. So magnetic field changes or increases, which results in an increase or change in the magnetic flux linked with the coil, and accordingly induced current is produced. Similarly, students, as the magnet is withdrawn or taken away from the stationary coil, then the magnetic field lines linked with the coil starts winding up, it starts decreasing. With the decrease in the magnetic field linked with the coil, the magnetic flux also starts decreasing. Again, induced current is produced due to the change in the magnetic flux. But now the direction of the induced current in the coil will be opposite to that in the earlier case. Right? So, in order to change the magnetic flux, we have various options. We can change the strength of the magnetic field. We can change the effective area of the coil under consideration. Remember experiment 3 which we have discussed in the previous section. So we have considered a uniform magnetic field, right? And we have considered a coil. So whenever the coil is moved inside the magnetic field, then everything remains constant. Area, magnetic field, the angle between B and A. So magnetic flux doesn't change. So there no current is produced. But when that coil is pulled away from the region of the uniform magnetic field, or it is made to come inside the region of the uniform magnetic field, then what happens is the effective area of the coil inside the magnetic field that changes, and due to the change in the effective area of the coil, the magnetic flux linked with the coil changes, and hence induced current is produced. Right? So, magnetic flux linked with the coil can be changed by changing the strength of the magnetic field. It can be changed by changing the effective area of the coil inside the magnetic field. It can be changed also by changing the orientation of the coil under consideration. Theta, as you are aware, is the angle between the magnetic field and the area vector. So students, these are the various methods through which the magnetic flux linked with a coil can be changed. And first law states that either way, whenever the magnetic flux linked with the coil changes, an induced current will be produced in the coil. Clear? This is the first law of electromagnetic induction. Now let us discuss the second law of electromagnetic induction. Students, again, let us recollect the experiments which we have discussed in the previous lecture, right? As you remember, if there exists no relative motion between the source of the magnetic field and the coil, then induced current in the coil is zero. That is, no induced current is produced in the coil. What I mean to say is that when the magnet, which acts as a source of magnetic field, is held stationary with respect to the coil, that is, when the coil and the magnet both are held stationary, then the galvanometer in the coil do not show any deflection, indicating that induced current is not produced. Also students, in the second experiment, in the case of tapping key, when it is kept pressed, when the current through the coil becomes steady, then in the neighboring coil, no induced current is found to get produced. Right? Because when current is steady, then a steady magnetic field will be associated with the neighboring coil. So magnetic flux linked with the coil will not change, and hence current is not produced. And in the third experiment, students, when the coil was moved well inside the region of uniform magnetic field, then strength of the magnetic field was considered to be uniform, so it remained constant. Effective area of the coil under the influence of the magnetic field, that also remained constant. Orientation theta, that also remains constant. So the magnetic flux linked with the coil, when it is moved well inside the uniform magnetic field, is found to remain constant. So in that case, again, no induced current is found to be produced in the coil. So all these observations led to the conclusion that induced current is produced in the coil as long as the magnetic flux linked with the coil keeps changing with time. So this is the second law of electromagnetic induction. So second law of electromagnetic induction states that the induced EMF or the induced current lasts or exists as long as the change in the magnetic flux or the change in the magnetic field continues. So this is the second law of electromagnetic induction. Now students, before we discuss the third law of electromagnetic induction, I would like you to go through this very interesting animation.
In 1820, Oersted discovered the magnetic effect of electric current. That is, when a steady current flows through a conductor, a magnetic field is produced around it. In 1831, Michael Faraday discovered the effect called electromagnetic induction, which is just the converse to the magnetic effect of electric current. Let us take a microammeter, a magnet, and the two coils, one of 100 turns and this coil to be of 25 turns. Let us first connect the ammeter to the coil having 100 turns. Now let us bring a magnet closer to this coil. Now whenever there is a relative motion between the source of the magnetic field and the coil, the ammeter shows some deflection, indicating the production of induced current. Now if it is held stationary in the absence of relative motion, no current is induced. And when the magnet is moved faster, that is, the relative motion is made faster, then the magnitude of the current is found to be also large. It is approximately 10 microampere. So faster the relative motion, the more is the magnitude of the induced EMF or induced current. Now let us perform the same experiment using a coil having 25 turns, that is 1/4 the turn which the previous coil was having. Now in this case, on moving the magnet, we find the deflection in the ammeter to be about 1/4 the deflection in the earlier case. Thus, from the experiment, we conclude that with the increase in the number of turns of the coil, the magnitude of the induced EMF or the induced current produced in the coil also increases.
I hope students you have understood the conclusions which were drawn while performing the experiment shown in the video, right? So what we have concluded is, as the relative motion between the coil and the source of the magnetic field is made faster, the magnitude of the induced EMF or the induced current also increases. So faster the relative motion, so more is the strength or the magnitude of the induced current so produced in the coil, right? And slower the relative motion, lesser will be the magnitude of the induced current produced in the coil. So students, again let me recapitulate the things which we have observed during this experiment. One is, as the magnet is brought closer to the stationary coil at a large speed, then what happens is the galvanometer showed appreciable deflection, indicating that the strength of the induced current is large. If the magnet is brought closer to the coil slowly, then the galvanometer shows deflection, but the deflection is very small. So in this case, when the relative motion is slow, then the magnitude of the induced current is also small. So faster the relative motion between the coil and the source of the magnetic field, greater is the magnitude or the strength of the induced current so produced in the coil, right? So students, the strength or the magnitude of the induced EMF, it depends upon time rate change in the magnetic flux linked with the coil. This is very important conclusion. The strength or the magnitude of the induced EMF is directly proportional to the time rate change in the magnetic flux linked with the coil. Time rate change means change in the magnetic flux divided by time during which that change in the magnetic flux has occurred, right? So this is the third law of electromagnetic induction. So let us state it mathematically. So suppose, let us consider a coil whose let the initial magnetic flux is phi I. This is the initial magnetic flux at, say, at t equals to 0. Let the final magnetic flux associated with the same coil is phi f after time t. So what is the time during which the flux changes from phi I to phi f? It is time t. So students, change in the magnetic flux, change in the magnetic flux associated with the coil is, change is always final value minus initial value. So time rate change. So time rate change in the magnetic flux associated with the coil is, it is change in the flux divided by the time during which this change has taken place. So here initially we have considered phi I to be the flux associated with the coil at t equals to 0, and after time t has elapsed, the new magnetic flux associated with the same coil is phi f. So time rate change in the flux would be change in the flux divided by the time during which that change has taken place. So what we have concluded through the experiment is that the induced EMF, let us represent it by small e. This is induced EMF, which is the EMF or the voltage which get induced in the coil due to the phenomenon of electromagnetic induction. I will represent it by small letter e, right? So it is directly proportional to the time rate change in the flux, which is phi f minus phi I divided by t. Clear, students? Now, as you are aware, in order to eliminate this proportionality sign, we need to introduce some constant. So E is equal to minus k phi f minus phi I divided by t. This minus sign represents that the induced EMF so produced in the coil is always of opposing nature. This we'll consider in fourth law of electromagnetic induction, which is known as Lenz law. So negative sign basically signifies the opposing nature of the induced EMF or the induced current. Clear, students? Now in SI, the value of K is found to be 1. Therefore, the magnitude of the induced EMF is equal to minus phi f minus phi I divided by t. And as I have stated, the negative sign suggests the opposing nature of the induced EMF. Clear, students? So this can be expressed in calculus as well. So in calculus, the induced EMF is given on minus d phi by dt. This is the time rate change in the magnetic flux. If the change in the flux takes place in smaller time, then the magnitude of the induced EMF would be large. If the change in the magnetic flux takes place in large time due to the slow relative motion, then the magnitude of the induced EMF would be small. So this explains why on faster relative motion the calculator shows more deflection, and when the relative motion is made slower, then the calculator shows small deflection, right? So this is the mathematical expression, E equals to minus d phi by dt. Also, students, in the experiment which we have just now seen in the small video, what we have considered was a coil of 100 identical turns, and in the second case we have considered a coil of 25 identical turns. In case of 100 identical turns, when the magnet was brought closer or it is taken away, the magnitude of the current found in that microammeter was about 10 microampere, right? While when the same experiment was done by taking coil of 25 identical turns and the magnet was moved at the same rate, right? There, the reading of the microammeter was found to be about 1/4. That is, it was about 2.5 microampere. So which clearly suggests that with the increase in the number of turns, the strength of the induced EMF or the induced current also increases. So what I mean to say is that if the coil consists of n identical turns, then the induced EMF will become n times. Greater the number of turns, greater will be the deflection shown by the galvanometer, which clearly suggests that larger the magnitude of the induced EMF so produced in the coil. So for n identical turns, the induced EMF is given by minus n d phi by dt. This is the time rate change in the magnetic flux, and n is the total number of turns. This is actually known as Faraday Lens Law. It is actually the mathematical form of Faraday Lens Law. Right? Negative sign, as I told you, it suggests the opposing nature of the induced EMF. We'll discuss Lenz law later on, right, in the coming session. Anyway, theoretically we'll discuss it in the present episode as well. So, third law is the magnitude of the induced EMF is directly proportional to the rate of change of the magnetic flux linked with the coil. And this is the mathematical expression. So students, what about the expression for the induced current then? Imagine the coil under consideration to be offering ohmic resistance R, capital R. Then the induced current would be given by E by R. So it will be equal to minus N by R d phi by dt. So this will be the expression for the induced current. Capital R is the resistance offered by the coil under consideration. Again, negative sign suggests the opposing nature of the induced current. If induced EMF is of opposing nature, then obviously induced current will also be of opposing nature, right? Again, before we discuss the fourth law, which is the Lenz law, which will indicate the significance of this negative sign, I would like you to watch this small animation.
Electromagnetic induction is the phenomena of production of electric current in a coil when the magnetic field linked with the coil or solenoid is changed. Let us consider the magnet with its north pole facing the coil to be moved towards the coil. As it produces a changing magnetic field, thus an induced current is produced in the coil, the direction of which is such that it opposes the approaching magnet. And as a result of the production of induced current, the galvanometer shows deflection. In case there is no relative motion between the magnet and the coil, then the galvanometer shows zero deflection. Now, if the magnet is moved farther away from the coil, then again, due to the decrease in the magnetic field linked with the coil, an induced current is produced. But now, the direction of the induced current is such that it opposes the receding magnet. So the galvanometer now shows deflection in the opposite direction. Therefore, we conclude that induced current is produced in the coil whenever there is a relative motion between the coil and the magnet.
I hope you have understood the video which you have just now watched, right? So, what we have seen is, if a bar magnet with its north pole closer towards the coil is brought closer, then what happens is, induced current will definitely get produced in the coil. But the direction of the induced current in the coil will be such that it opposes the approaching magnet. And that is, suppose this is the coil, right? And this is the magnet. Let the north pole of the bar magnet be closer to this coil and the magnet be brought closer to this stationary coil. Now what happens is, as the magnet is brought closer, the magnetic field lines linked with the coil will grow definitely. So due to the change in the magnetic field, due to the change in the magnetic flux linked with this coil, an induced current will get produced. Now Lenz law states that the direction of the induced current in the coil will be such that it opposes the causes that produces it. So induced current is produced due to the increase in the magnetic flux by the approaching magnet. So here the induced direction, the direction of the induced current will be such that it opposes the approaching magnet. And that is possible only when this face which is towards the approaching magnet must acquire north pole. That is, it must acquire the same polarity as that of this end of the bar magnet, so as to repel it, so as to oppose the approaching magnet, right? So this end will acquire north polarity and the other end must acquire south polarity, so as to oppose the approaching magnet. Always remember, students, the direction of the induced current so produced in the coil will be always in such a direction so as to oppose the changes or the causes that produces it. Due to the approaching magnet, the induced current is produced over here due to the change in the magnetic flux. So the direction of the induced current in the coil must be such that it opposes the approaching magnet. And it can oppose only when this face of the coil acquires same polarity as that of the polarity of the nearer end of the power magnet. Right? Similarly, let's consider another case. Like, let's consider the same coil, and over here the magnet, the same magnet is made to move away from this stationary coil. Now, as the magnet is taken away or it recedes from the stationary coil, what happens is the magnetic field lines through the coil starts winding up, it starts decreasing. So due to the change in the magnetic field or due to the change in the magnetic flux linked with this coil, again an induced current will be produced. And as per Lenz law, the direction of the induced current will be such that it opposes the changes or causes that produces it. In this case, the magnet is receding away. So the direction of the current in this coil must be such that it opposes the receding magnet. It can oppose the receding magnet only when this face acquires polarity opposite to that of the polarity of this magnet. So this end or this face must acquire south polarity, while the other face must acquire north polarity, so that it will actually tend to attract the magnet so as to oppose the receding magnet. So in whatever case, the direction of the induced current in the coil must be such that it opposes the changes or the causes that produces it. If the magnet is brought closer to the coil, then the direction of the induced current in the coil will be such that it will oppose the approaching magnet. If the induced current is produced in the coil due to the receding magnet, then the direction of the induced current in the coil will be such that it opposes the receding magnet. So that forms the Lenz law, right? Which states that the induced current produced in the coil always flows in such a direction that it opposes the change or the causes that produces it. So this was basically given by Lenz, and accordingly it is known as Lenz law. It is known as Lenz law. And these four are collectively known as laws of electromagnetic induction. So this negative sign suggests that the induced EMF or induced current is always of opposing nature. Do remember that. Induced EMF or induced current is always of opposing nature. The direction of the induced current in the coil is such that it always opposes the changes or the causes that produces it. Whatever might be the reason for the production of the induced current in the coil, the direction of the induced current in the coil will be such that it opposes that cause. Clear, students? So, we will end this session here, and in the very next lecture, we will be discussing Lenz law in detail, where we will be solving several conceptual questions, and we will consider some various other examples as well. Right? So, join me in my next lecture, and till then, goodbye, and do take very good care of yourself. Thank you.